So this is the Jornadas de Matemáticas de la Zona Sur. And today we will have 3 talks in our discrete mathematics session. And I will leave you with the first speaker. She is from the Université de Bordeaux. I don't know if I say it correct. Her name is Marthe Bonamy, and she will talk about on a recoloring version of Hadwiga conjecture. So thank you very much, Marthe.
Muchas gracias, Andrea, para la invitación y la organización. No hablo español muy bien, así voy a hablar inglés, lo siento. So, so as Andrea said, I'm going to talk to you about something called the recurring version of Hadwiga's conjecture. So don't worry if you don't know about recurring and you don't know about Hadwiga's, because I'm going to explain both of those notions. So hopefully everything should be clear. So if you have any question, or I'm not talking slowly enough or something, then feel free to interrupt and I will slow down or repeat stuff. So this talk is about graphs. So you have a graph, simple graph, you don't have any multiple edges, you don't have orientations or anything, it's just as simple as you can imagine. And we really focus on connected graphs. So you can assume your graph is really in just one piece. I mean, if you have different pieces, you just focus on each piece independently, so it doesn't really matter. So you have a graph like this, connected graph again. And so this is about the recurring. So let's first talk about coloring. So how do you color a graph? Well, you assign colors to every vertex. And you just have the constraints that 2 vertices which are adjacent should have different colors. But I don't really want to tell you about coloring, I want to tell you about recoloring. So how do you recolor a graph? So what you're going to do is you're going to take 2 colors, your 2 favorite colors. So let's say here for now, your 2 favorite colors are blue and green. So now you look at the graph induced, the subgraph induced by these 2 colors in your initial graph. So here, when you look at the subgraph induced by colors blue and green, that's this path on 4 vertices. And so you take a component. Well, here you don't have a choice, there's only one. So you take this path on 4 vertices, and you swap the colors there. So what you get is a new coloring. It's still proper, because in the way you swap colors, there's no way you can create 2 adjacent vertices with the same color. So it's still a valid coloring. You didn't introduce any new color or anything. But it's a bit different from the initial coloring. So here you can see, you swap colors blue and green. So a bit more formally, this notion of Campechain, when I said you take your 2 favorite colors and you look at the subgraph induced by these 2 colors in your initial graph, and you take a component, that's precisely something which is called a Campechain. And something called a Campechain, so that's how we recolor the graph. It's really just taking a Campechain and swapping the 2 colors there. So let's do a few more examples just to make sure everything is clear. So initially we say that 2 favorite colors are blue and green. Let's change our mind and say now 2 favorite colors are red and green. So now when we look at the graph induced by red and green here, you have 2 parts. You have this part on 2 vertices here on the top, and you have this single vertex at the bottom. So when you have to pick a component, you can pick the top one, this edge colored red and green, and you can swap colors there. So you can see this single green vertex on the bottom, like it didn't change. You're really just taking a single component and swapping colors only there. So this is a coloring you can reach from that using just one single Campechain. But you could also have taken the other component. So you could have taken like the single green vertex, which is alone. So it does not have any red neighbor. But you can still do a Campechain there. So what does it mean doing a Campechain on a Campechain, which is like just a single vertex? It just means you give it a new color, which doesn't appear in its neighborhood. So here you just get this new coloring. So again, we started from a 3 coloring of this graph, which is a cycle on 5 vertices. And we have this operation called Campechain, which allows you to kind of navigate the space of colorings of the graph. So here, I'm not sure how obvious that is, but you can convince yourself that if you start from this coloring and you allow Campechain as a basic operation on the colorings, you can reach any given 3 coloring of the cycle on 5 vertices. So in general, like, why do we care about this operation? So initially, I mean, it was introduced by Kempe, as you can guess from the name. And the reason he introduced it, so it was ages ago, it was in 1879, so almost, before graph coring was much of a thing. And as you can guess from the time, it was introduced as an attempt to prove the four-color theorem. So it did not quite work. I mean, it's still some tool which is useful in the proof of the four-color theorem. It was not enough by itself to prove the four-color theorem. But yeah, it turned out to be an interesting way to, again, navigate the space of k-corings for any given k of a graph. So if you start from somewhere, try to modify things and see how far you can go, if you can reach all the corings, or if there are some things that block you. So I'm going to discuss a bit more later why this is useful. But let me tell you more about what we can say. What are the positive things we can say about this operation? Like, when does it work well? So here for C5, I said, you can convince yourself that all the three corings are equivalent in this notion, meaning you can go from one to the other through a series of such basic changes, Kempe changes. Is this something which is true in general? So whenever you do coring, usually one of the first few theorems you see about coring is related to the maximum degree of a graph. So it's something you usually denote the delta, so this symbol here on the top. So it's just really the maximum number of neighbors a vertex can have. So it's really maximum degree of the graph. And one of the first, well, the very, very first results you see in this topic is just saying, if you do greedy coring, so, take the graph, order the vertices arbitrarily, and for every new vertex you look at, just give it a new color, meaning, not new color, sorry, the smallest color not using its neighbors, which are already colored. So this tells you for sure, whenever you have a graph, you can always core it with delta plus 1 colors. That's an upper bound. I can always get that for free in a greedy way. And the first non-trivial result usually here in this direction is Brooks' theorem. So from 1941, which is actually for most graphs, you can do one better. So namely, if your graph, remember, I'm only talking about connected graphs, because otherwise, the statement would not be quite true, but your graph is connected. If the graph is not a clique and it's not an odd cycle, then actually you can do a bit better than delta plus 1, meaning you can find a delta coring. And you can check easily that if you're a clique, then you cannot get that. And if you're not a cycle, you cannot get that. But otherwise, you can get just like you find delta coring. So yeah, this is one of the first theorems you hear about when you do coring, when you try to see what kind of upper bound you can have, what kind of non-trivial upper bounds you can get on the number of colors you need to color the vertices of a graph. So now that I told you about this way to navigate the space of corings and stuff, one thing you can wonder is, okay, this theorem tells you there is one delta coring. So what about the others? How do they compare to any given delta coring, with this basic operation of Kempe changes? There was a really nice conjecture by Boyan Mohar from 16 years ago now, saying that actually they should all be Kempe equivalent, meaning take your favorite delta coring of your favorite graph, just through a series of Kempe changes, you should be able to reach your second favorite, always. It's really a beautiful conjecture. It's very intuitive in some sense. Like, given Brooks' theorem, Brooks' theorem, I don't know if you've seen a proof of it, but it's really easy to prove. Like, there are a few tricks to know, and there are many different ways to prove it. So you'd feel like there's enough margin of error that you should be able to prove Boyan's conjecture. The only bad news, this conjecture stayed open for a long time, and then 7 years ago, Jan van den Heuvel actually proved, unfortunately, this conjecture is false. And this counterexample is interesting for the rest of the talk, so let me spend some time explaining why this is a counterexample. So you have this graph, and the same graph on both sides, just a different coring. So it has max degree 3. Everyone has degree precisely 3, so max degree 3. And the interesting property here is that whenever you take two colors, say blue and red, it doesn't matter, the subgraph induced by these two colors is connected. So it's true for blue and red, it's true for red and green, it's true for blue and green. Together, you can always check it's always connected. So what this means is that when you do a Kempe change, you don't change the color partition. Meaning you technically, yes, you change the coring, but the two vertices which had the same color still have the same color, and two vertices which have different colors still have different colors. So you can go, as far, you can proceed for as long as you like, you're still not going to escape that. And on the right, you have a coring which is the same property. So again, any two colors in this connected subgraph. So again, you cannot escape the color partition, but the color partition is not the same in the left and on the right. So what you can see is this blue guy on the bottom and this red guy on the bottom. They have different colors on the left, but they have the same color on the right. So there's no way you can go from one to the other through compute changes. So that was really sad. I mean, I remember hearing about this example from Jan, and I was really, feeling life is unfair, and this conjecture should have been true. And the good news is it's almost true. Meaning, if you look at graphs which have max degree at most 3, this is the only counterexample. So it's, encouraging again. You feel like, okay, it was a nice conjecture, and there was this nasty counterexample which you did not want to believe in, but at least it's the only one for small degree. So then the question was, okay, how does this behave when you go to higher max degree? Like, do you still have one counterexample for each value of max degree, or does the number explode as delta goes up? And the big surprise, I mean, I'm not sure it was a big surprise to everyone, but it was a big surprise to me, is that there is no other counterexample. Meaning, Mohart's conjecture is true for all graphs except for this one. It's not except for all, it's not true for all graphs except those which contain that one. No, it's really specifically this unique graph on 6 vertices. So it's kind of funny. It's not always you have a conjecture with just such a single, well-defined counterexample. So that's interesting. So it says, you have this Brooks theorem, which tells you there's always some delta coring. Unless your graph is really specific, like a click or not cycle. So you can always find some delta coring. And what this theorem says is that actually all the delta corings are equivalent up to compute changes, unless your graph is this very specific one on 6 vertices. And actually the proof is not that bad. Still 20 pages also making sure everything works out. But the idea behind is really just Brooks' theorem. I'm lying a little bit, but not that much. And another thing which is funny, so for a long time I wondered how many steps you need to do this series of compute changes. So we know there is a way to change the coring step by step and eventually reach your second favorite delta coring. And it was really, really not clear from the proof how many steps you need. The proof gave you an exponential bound on the number of changes. So you knew you need at most, I don't know, 2 to the number of vertices compute changes, but that's not a very good bound. And very recently with a student of mine and a colleague, we were able to prove that actually it's not just that they're equivalent, but they're equivalent up to few compute changes. Well, few is not, let's say, that few, but it's still at most quadratic in the number of vertices. So polynomial. Really, we only care about is it exponential or is it polynomial? And now we know it's polynomial. So it's, it could be worse. That's the translation of this. So I told you I would say a bit more about why we should care about compute changes. The reason I care about compute changes is because it's fun. Because it's kind of interesting to see how different corings in the graph compare to each other, like how much freedom you have in each coring. But there's some actual motivations for it. Applied motivations for it. So it turns out that understanding how corings compare with respect to compute changes actually helps you understand some stuff in statistical physics. So you have some model about how electrons behave when temperature drops to 0. Well, not drops, but gets close to 0. And to my surprise, compute changes actually help you understand that. And that's not even that's a real motivation for looking at global dynamics. So this, what happens when you look at how much you need to change corings to get from one to another. So yeah, there's a whole series of papers in literature linking the two and trying to understand one to understand the other. And the thing which is a bit sad is here you have this kind of neat picture, like uncoordinated picture, when you allow delta colors. And as soon as you have fewer colors involved, everything gets a lot messier. It's hard to give a nice, neat theorem saying, whenever you have number of colors at least, I don't know, twice comet number, everything should be fine. Like nothing like that is true. So it's a bit depressing at first, because this is encouraging in the sense that it's nice. You kind of want to extend this to, you know, stronger settings or things with fewer colors. And it's really hard to do that. But let me tell you about some attempt to do this. So another old conjecture that some of you might have heard about is Hadwiger's conjecture. So it's from 1943, and so it's again about coring. And one important notion for Hadwiger's conjecture is notion of minor. So you say a graph contains minor and t vertices if you can find in a graph t connected blobs which are pairwise adjacent. I mean, there's just like between any two blobs, you should have some edge. It doesn't have to be further constrained than that, but you should have t disjoint blobs, and between every pair there should be at least one edge. So that's KT minor. So that's when the graph contains a clique on t vertices as a minor. So it might sound like a weird notion, and that's this conjecture from 1943 saying, well, there's this weird notion of containing a clique on t vertices as a minor, and if you don't contain that, and if you don't contain a clique on t vertices as a minor, then you should be colorable with very few colors, and few is t-1. So it's kind of interesting because, I mean, it might seem, if you haven't heard about this before, this might seem really counterintuitive. Like, why should these two things be related? I mean, clearly you can be t-1 colorable even if you contain a very large clique as a minor, because, I mean, a bipartite graph can contain a very large clique as a minor, and it's still too colorable. But so essentially, very briefly, the motivation for this conjecture is that, I mean, you'd like to tie the number of colors in a graph with some structural parameter. So the naive thing to try is try to bound it as a size of the largest clique in the graph. And that fails miserably, meaning you have graphs which don't contain a clique on 3 vertices, so they don't contain a triangle, and they still have arbitrarily high comet number. So, you know, finding a clique as a subgraph is not the right way to bound the comet number. And essentially, minors are the best candidate we have for this. And what's funny here is that this conjecture, so this really old conjecture, has been confirmed to be true only for t at most 6. And if you fail to see why this is hard, think about the case t being 5. If you think about the case t being 5, it says any graph with no k5 minor is 4 colorable. And if you think about it, when you have a k5 minor, you cannot be planar. So every planar graph, I mean, so it's something stronger than saying that every planar graph is 4 colorable. So this conjecture in the case t equal to 5 implies the 4-color theorem. So you can imagine, you know, case t being 6 and then t being higher. But anyway, so we have no idea if this conjecture is true in general, like for high t. But in the recurring setting, there's this recurring version of it, which says, okay, we don't know if there is a t-1 coring, but what we think is that regardless of whether there is one or not, all the t corings of this graph should be Kempe-equivalent, meaning you should be able to navigate the space of t corings, which could be empty, we don't know, but if it's not empty, you should be able to go from any one to any other through a series of Kempe changes. So this was a conjecture from Las Vanias and Meniel from 1981. And here again, you can say some small things. You can say it's true for t being at most 5. And again, this has implications for planar graphs. So if you look at t being 5, it says that all the 5 corings of a planar graph are Kempe-equivalent. So it doesn't mean there is a 4 coring. It just means that if you start from a 5 coring, through a series of commutations, you can go to any other 5 coring, and in particular, you can reach a 4 coring if there is one. And we know through other reasons that there is one. But anyway, so just trying to emphasize that this is related to Hadwiger's conjectures. It's like, it's really a recurring version of it, but it doesn't imply it and it is not implied by it. It's really independent. It just has the same flavor. And the main result I want to tell you about is that this is unfortunately really false. So that's something we proved with Marc Heinrich, Clément Legrand, and Jonathan Arboni, actually a month ago, essentially. It's that You can find examples of graphs which don't contain, so I mean, essentially in this conjecture, for this to work, you have to replace no kt minor here with at least k 2/3 t minor, say. So it's really, really false. Like even if you drop a bit the decrement, or if you get this the other way around, even if you increase quite a bit the number of colors, I mean, if you allow almost half as many colors extra, you still cannot necessarily find a series of computers to go from any coloring to any other. So it's really saying this conjecture is strongly false, unfortunately. It would be really nice if it were true, but it seems like we have many counterexamples to this conjecture, and they're not just barely false, they're really false. Let me very quickly say a few words about roughly how we prove that. So just in a few words, you take a clique, you replace every vertex with two non-adjacent vertices. So essentially between any two vertices in the old clique, you get now something like this, like you replaced every vertex with, so this was an edge initial clique, and now you added just basic vertex with two non-adjacent vertices. And for every pair, you throw a coin and you delete one of the four edges at random. So this is kind of, G and a quarter model, except like it's kind of biased, meaning if you delete that edge, then you're not going to delete any of the other three. So you delete precisely one edge for each four. And what's funny, well, I'm not sure it's funny, but what's interesting is that when P is large, with high priority, this does not contain any large minor. So any minor of size more than 2/3 of P, essentially. But you have a P coring which is frozen. And by frozen, I mean exactly what we had with this counterexample to Mohar's conjecture, meaning that any two colors induce a connected subgraph, so that when you swap colors, you don't change the color partition. And you can find that there are distinct coring, so that's it. Like, that's the corings are not all completely equivalent. And just because I find this funny, even though it's not completely related to this thing with Hadwiger's conjecture, I just wanted to say a few words about in which other places compare changes are useful. So something which some of you probably know, but maybe not all of you know, so I kind of want to advertise this as a thing, is that compare changes are really crucial behind the proof of Wissing's edge coring theorem. Like all the proofs we know of Wissing's theorem, they use compare changes in a decisive way. So what's Wissing's theorem? So it's from 1964, and it's about coring the edges of a graph. So it's just like coring vertices, except now you color edges. You don't want incident edges to have the same color. And Wissing's theorem says that, again, the number of colors you need is tied with the max degree of the graph. So it's always at most max degree plus 1. And you can see easily max degree is a lower bound. Because if you look at the vertex with max degree, then you need distinct colors for all of the incident edges. So this theorem, I mean, it's trivial that delta is a lower bound, and this theorem says that delta plus 1 is an upper bound. And so yeah, all the proofs we know are through compare changes, and compare change for edge coring is the same as for vertex coring in the sense that you just take two colors and swap them. So you can here, I mean, it's really exactly the same thing going on, because I mean, for a C5, edges of it are the same. But anyway, just to get an idea of what's going on. And what he actually proved is you can start from your favorite edge coring, doesn't matter how many colors are involved, and just through a series of compare changes, you're eventually going to decrease the number of colors involved so that you eventually end up with a delta plus 1 edge coring. So that's really what he did in his initial 1964 proof. So really start from anywhere, through a series of compare changes, you can go down to delta plus 1 edge coring. And his conjecture, which I really like, is that actually, I mean, sometimes for some graphs, delta colors are enough to color it. And his conjecture is that, well, then you should also be able to reach that through a series of compare changes. And that's far from obvious. Like, so, I mean, there's been some partial results saying, for graph with small max degree, this works out and stuff like that. And what we proved recently with Oscar Defrin, Terka Klemoshova, Aurélie Lagoutte, and Jonathan Arboni is that if your graph is actually triangle free, then that's true. So start from your favorite edge coring. You can go down to an optimal edge coring. So edge coring using well, delta plus 1 colors if you need that many, or delta colors if that's enough for you. And so it's a bit stronger because it says as long as you have a little, well, at least one more color than the target coloring, you can even choose your favorite target coloring. So yeah, just to advertise a little bit this can be changes. So this is really about you have this way to navigate the space of colorings in a graph. So initially it was a tool to prove things, to prove the four-color theorem. It did not work directly, but it was still helpful. It's also crucial in the proof of Wissing's edge scoring theorem. And I hope I convince you, at least to some extent, that it's also kind of fun to see what it means in the space of colorings. Like, is the space of coloring connected? Like, what does this tell you about the structure of the graph? And when it's connected, like, how many steps do you actually need to get your favorite coloring? And that's it. Thanks a lot.
Oh, thank you very much. Is there any question?
Yeah, quick question. Do you have an estimate in the diameter in the case of edge coloring?
So for edge coloring in Wissing's proof, you get a number of times number of edges, number of steps. And in our proof, I forgot the exact thing we get, but it's a polynomial in the number of edges.
Okay,
but it does
thanks.
not mean we can compute in polynomial time an actual, optimal coloring, because I mean in the proof we assume we have access to an optimal delta edge coloring, and we get down to that, but using knowledge. So it just tells you there's a short path. It doesn't tell you how to get there.
Okay, thanks.
Sorry, and is there any like lower bound for the number of switch you need? Like, is it clear that it should depend on n, for example? I mean, or it might just be a function of the maximum degree, or?
So that's really tough. So essentially, I mean, if you want to convince yourself that n is a lower bound, what you can do is just take like, a bunch of isolated vertices or edges. And if, the coloring differs on all of them, then you need at least n steps. But that's the best lower bound we have. Like, we don't have any non-stupid lower proof that you need something linear in n. And actually, it's a pet, I'm not going to say conjecture, but pet theory of mine, say, that it should always be linear in n. Like, I can't imagine a case where you need to get more than linear number of steps, but even proving polynomial number of steps is usually hard. So it's not worth much. But yeah, it's a big question. Like, we really lacking tools both for lower bounds and upper bounds.
Sorry, but I mean, and moreover, like what you prove is not enough to prove like rapid mixing or something in clouded dynamics.
So,
right?
rapid mixing is stronger, right? You need not just small diameter, and it's a prerequisite, but you also need like high connectivity and a bit more. So yeah, what we prove is not enough. And well, for rapidly mixing, the best known is like 11/6 of delta. I mean, a bit less than that, but whatever. So yeah, we're really far away from getting that for delta colors. But yeah, that would be super lovely.
More questions?
So the conjecture of Las Verñas, so that failed. Would you restate that conjecture in some way?
So
would you make a new conjecture?
So I'm not sure if I believe it or not, but I think a nice question is there some constant such that all the some constant C such that all the CT colorings of a graph with no manner can be equivalent? And that would be nice, because as soon as you have C being at least 2, clearly, I mean, you can convince yourself that there is no frozen coloring. So if it's not connected, then it's for a reason other than something, having the same partition. And kind of like we lack tools for lower bounds, we don't know of any way to prove something is not connected other than saying that here's this frozen coloring. So that's, I mean, I would love to see an answer to this question one way or the other. I'm not sure which one I would prefer, but I would be super happy with either.
Okay, thank you.
Sorry, and there was one thing about the Whiting's conjecture that I didn't understand. So like the one before last. So you said that there's an alpha, but then there's a proper delta plus one edge covering. So alpha is delta plus one edge covering, or?
So alpha can use arbitrary many colors. It's just that when you do Kempe change, you know, I said that sometimes you can have an edge where you don't have any other incident edge of, sorry, take your two favorite colors, say red and blue, and if you can find a red edge, which does not have any incident blue edge, when you do a Kempe change there, the red becomes blue and sometimes you got rid of the red. So that's how you can decrease the number of colors involved in the graph.
Oh, okay.
So that's what's going on here. So essentially what he does is that he looks at every one of the maximum color that he wants to get rid of, and then he step by step decreases the number of edges of that color until he gets to 0. And then he starts again with the second biggest color and so on until you reach delta plus one colors.
Okay, thanks.
Thank you again, Marthe, for the nice talk. And if there is other question, you can ask Marthe directly. Porque estamos en una charla, hijo, y lo hizo muy bien. Mira, ella habló. Por eso estamos.
Wow, ¿tantos?
Sí. Yeah, we are many here. Yeah, that's nice. Sí, somos muchos, mira, 26.
Wow.
Okay, to continue with our program. And now is the turn of Adrian Pastine. He's from Universidad de San Luis, from Argentina, and he's going to talk about diameter of Shriver graphs. So please, Adrian.
Thank you, Andrea, for the invitation. And I'm not sure, are you listening? Yeah, sorry. Thank you, Andrea, for the invitation, and thank you everyone for being here. As Andrea said, I'm going to be talking about the diameter of Shriver graphs. I'm going to be using a bunch of words that I'm not sure how to pronounce them, so sorry about that. This is joint work with Pablo Torres from Universidad Nacional de Rosario, also here in Argentina, and Mario Valencia Pavón from Université Sorbonne Paris Nord. This is one of the things that I don't know how to pronounce, in France. I'm going to start with some basic definitions. Oops. There we go. So in order to talk about Shriver graphs, we need to start with Nisser graphs. So the Nisser graph on N and K has as vertices the K element subsets of a set of N elements. And here we're going to actually label those elements 1 through N. And an edge between two vertices if the corresponding sets are disjoint. So there is a typo there. So for instance, this will be KG phi 2. These are all the two subsets of 1 through 5. 1 and 2. 1, 2 is disjoint from 3, 5. So there is an edge there. 1, 2, 3, 4, and 3, 4 are disjoint. 1, 2, and 4, 5 are disjoint. So there are some edges there. And those will be all of the edges. So this is actually a quite known graph. It's a Peterson graph. And as I was saying, all the proper names I'm probably going to mispronounce. Right. So the Shriver graph is a vertex critical subgraph of the Nisser graph that has the same coloring number. It was introduced by Shriver in 1978. And what you do is you take the Nisser graph and you remove vertices that have consecutive elements. So here we have to remove 1, 2 because the elements are consecutive, 3, 4. And you actually do this cyclically. So the last element and the first element are considered consecutive. So you also remove 5, 1, 2, 3, and 4, 5. Oops. So this will be the Shriver graph on 5 and 2. So now we have one of the two basic definitions that we need for the talk. The other thing is to talk about diameter. Probably most of you already know what this is, but the distance between two vertices in a graph is the length of a shortest part between them. So for instance, in this graph, which is Shriver A3, between vertex 1, 4 and 2, 4, we have this path that has length 3, but we also have this path that has length 2. And since the two of them are not neighbors, then the distance is the shortest. It is going to be 2. The diameter of the graph is the distance between the two vertices that are the furthest away from each other. So here, the longest distance between any pair of vertices is actually 2, because vertices on this inside graph, this is a complete bipartite, so there are either neighbors or a distance 2. Then the guys on the outside are all neighbors between them, and going from the outside to the inside, they're either directly connected or they go to one of the other outside guys and then go inside, and then you have a path connecting them. So here the diameter will be 2. So we are interested in studying the diameter of Shriver graphs. For a bit of history, Mario Valencia Pavón, which is one of the co-authors, and Juan Carlos Vera in 2005 studied the diameter of the Neisser graph, and they actually found a pretty nice formula for it. And this is actually a quite nice and short paper. I think it's like 3 or 4 pages only, but it's quite concise. And what we found is not as nice as this. So for us, the diameter of the Shriver graph is going to be 2. Sorry, maybe I should stop a little bit with the notation. So we are considering 2k plus rk. And here, you only need to consider r at least 1, because otherwise the graph is not connected. It's going to be 2 if r is big enough. So that is if r is at least 2k minus 2. 3 if r is between k minus 2 and 2k minus 3. When r is exactly 1, the diameter is k. This is actually quite easy because you are left with just a cycle. That is the case that we got with SG52. And now for the not so nice part of this result, is at least 4 and at most k minus r plus 1 if r is between 2 and k minus 3. So I'm going to tell you a little bit about the basic strategy that we're going to be following. So typically for these things is, if you want to find an upper bound, you present a way to find a path between any pair of vertices of such length. So for this, I'm going to show you a way to find a path of a length at most k minus r plus 1 between any pair of vertices. Then for a lower bound, you need to find a pair of vertices that are exactly at that distance, that they have no path shorter than that joining them. And that's what's hardest for us on this case here, right? So let me show you how we are going to be representing vertices. So now for this example, we are looking at SG27. That means that we have 20 elements in our base set. And the vertices are sets of 7 elements. So here we have 2 vertices, A and B, that I'm just going to place there. I'm coloring blue the vertices in B and red the vertices, blue the elements in B and red the elements in A. Notice that because we are working with a Shriver graph, that means that we cannot have consecutive elements in a single vertex. So this means that we cannot have 2 red consecutive or 2 blue consecutive. And also we have some intersection between A and B, otherwise they will be neighbors. What I'm doing is coloring purple the intersection between A and B. Now, what we are going to try to do now is find 2 vertices, A star and B star, that are A star neighbor of A and B star neighbor of B. And if possible, that the 2 of them are neighbors, so disjoint, or at least that the intersection between them is smaller than the intersection between A and B. So what we're going to do is we are going to place everything that is in B and not in A, we are assigning that to A star. Everything that is in A but not in B, we assign that to B star. Now, once we reach this point, the elements that are next to things that we already assigned to B star cannot be assigned to B star, so we are going to assign those to A star. In the same manner, whatever is next to something in A star, we assign to B star. And so I want to, well, I'm gonna stop here now, but what you may see now is that we get some of these white squares that are surrounded by a B star on one side and A star on the other side that we cannot use at all. And the other thing that I haven't assigned is whatever is surrounded by purple, because these are both in A and B. So again, I cannot use whatever is in purple, but I can use pretty much freely whatever is between them. So, and the other thing that we have in this particular example is that B star already has 7 elements, so B star here is a vertex. What we're going to be doing usually is, well, we reach this point, and then whatever is between purple, we use to complete A star and B star so that they are vertices, and try to do it so that the intersection is as small as possible. Now for A star, I have 2 possible choices, but I already had 6 elements there, so I only need to assign 1, and that's another vertex. So now A star is adjacent to A because they are disjoint, B star is adjacent to B, and we are lucky enough, A star and B star are neighbors of each other because they are disjoint as well. So here the distance between A and B is at most 3. Of course, we could have tried to find some vertex that is neighbors of both A and B. For those, we need to consider the blocks of consecutive white squares. And here we have, luckily as well, also a vertex that is disjoint both from A and from B. So actually the distance between A and B is 2 and not 3 as what we said initially. So now from here, what I want you to take from this is the importance of the blocks of consecutive blue and red squares, the blocks of purple squares, and we also have some interest, well, there is some importance in the block of consecutive white squares. So having shown you that, and that is more for intuition so that I guess it's easier to follow than anything else, we are already ready to sort of prove the first equality. That is that when R is big enough, the diameter is 2. So we are considering SG2K plus RK, and we have R at least 2K minus 2. That means that 2K plus R is 4K minus 2. Since we want to find the diameter, we want to consider 2 vertices that are not connected. Otherwise, the distance between them will be 1. That means that we can consider that the vertices A and B are not disjoint. The intersection is at least 1. But that means that we have at least, since A union B now has at most 2K minus 1 elements, that means that we have at least 4K minus 2 minus this, so that's 2K minus 1 elements left. If we have 2K minus 1 elements left, that means that at least K of them are, we can choose at least K of them that are not consecutive, right? Because if we have an odd block of consecutive white squares, we can use the ceiling of that length divided by 2. So that divided by 2 plus a half. And if it's an even number, we can use half. So that means that because of this being an odd number, we can use ceiling of this divided by 2 at least, which is K. So we have a vertex that's adjacent to both A and B, and that means that the diameter is 2. So that was the easy case. Now, if we want to consider R smaller than that, we need to pay a little bit more attention to the blocks. And now we are in the point where we actually consider this A star and B star thing. So we are going to have blocks that are surrounded by purple vertices, which we call type 1, type 2 that have, type 2A, sorry, that have a purple vertex, a purple element on the left, and an element in A on the right. Type 2B, the same, but B on the right. Type 3 is sort of the opposite. And then the annoying ones are the type 4 blocks that have either red on both sides, blue on both sides, or red on one side and blue on the other. So all of these types 2 and 3, we are not going to be focusing much on them on this talk because they are part of some of the technical lemmas that I'm not gonna be discussing. But basically what we're gonna do to find A star and B star is what we did before. We start assigning whatever is in A minus B to B star, whatever is in B minus A to A star, and then neighbors of whatever is in A star to B star, and whatever is in B star to A star, and so on. And now here is what, and when we finish doing that, whatever is in type 2 and type 3, we assign completely. So those are the nice blocks, as I was saying. Whatever is in type 4, we assign most of it, but we have these issues. When we have an even number of squares in a type 4A or type 4B, we cannot assign everything there, right? We have B star here, A star here, and this one we cannot use. And when we have an odd number in type 4H, again, we cannot really assign everything because we have to leave one out, right? A star and B star. So the technical lemmas that I said we are not going to be talking about say basically that using all of the type 2, type 3, and whatever you can use in type 4, you get enough things in A star and B star so that you can fix things using type 1. So type 1 is what we do, what we use to sort of complete what we had there. And we had a special type of type 1, which is short type 1, which is surrounded by purple, that has only one white square in there. So the result that we prove, and this is just counting things, counting how many things have to be in each of each type, is that we have two sets A star and B star that are A star is disjoint from A, B star disjoint from B, and the intersection of A star and B star is at most the amount of short type 1 blocks. Right, so that's why I specifically show you that type of block. The good thing about this is that since type 1 blocks are surrounded by the intersection of A and B, the intersection of A star and B star is actually going to be less than the intersection of A and B. Right? Maybe let me go here. Right, because you have intersection on both sides, so that means that it's sort of doing a path, right, and counting edges instead and vertices. So the distance between A and B is going to be at most 1 plus 2 times A intersection B. That is just applying this construction enough times until you get completely, you obtain two vertices that are disjoint. And furthermore, if you don't have any short type 1 blocks, the distance between A and B is at most 3 because we have A star and B star that are disjoint. And then the other two corollaries that we're going to use are that if we have any outside vertex Y, the distance between A and B is at most 2 plus 2 times the sum of the sizes of the intersections. That is just applying this corollary for A and Y and B and Y. And the last thing is that just by counting how many blocks of type 1 we have and sizes, using this we directly get that the diameter of SG to K plus RK when R is between K minus 2 and 2K minus 3 is, well, it's at most 3. So I haven't shown you yet the example of vertices that are not at distance 2. But we get that it's at most 3, and I'm going to show you that example later. So that actually leaves just the hardest part, which is what happens when R is between 2 and K minus 3. The strategy that we use here is we start with two vertices A and B, And what we're going to be doing is using operations to lift the vertices to a graph with a higher base set. And afterwards, we're going to come back to this graph. So we're going to use these two operations that I'm going to show you later that give us vertices in SG2K plus R plus 1K. And we are going to be applying these operations successively until we obtain vertices AP and BP in 2K plus R plus PK at distance at most 3. Once we do that, we are going to be coming back to SG2K plus RK. But now, yeah, so first notice that P is at most K minus R minus K minus 2 minus R, because once we reach this, we get 2 plus K plus at least K minus 3. And that we already know that has diameter at most 3. Now, we have two possible cases. The distance between AP and BP may be 2 or 3. If it's 2, we are going to find the vertex Y such that the intersection between A and Y and B and Y is at most K minus R minus 1 divided by 2. And now using that corollary that I showed you before, we get the distance that we want between A and B. Or when the distance is 3, we're going to produce two different vertices, A star and B star, such that the intersection between them is at most K minus R minus 2 divided by 2. And now again, applying that, the other corollary from before, we get the distance that we want for A and B. So now this is sort of what we're going to be doing now. I'm going to show you these two operations. So for this, we're going to work on this example, SG157. And we are going to be considering what happens when the distance between AP and BP is 2. So here, what we are going to be considering are the blocks of consecutive alternating colors, red and blue, that have length at least 3, and then short type 1 blocks. We're always going to start with a plus operation that takes one of these blocks of consecutive alternating colors and separates the first 2 of those elements from the rest. So what we do is we add a white square here and push everything to the right. Then we use the up operation. Notice that this forms a type 4H block. Right, so with that A star and B star, this is a place that we are never going to use. Then the other operation that we have, the up operation, what it does is it doubles the size of a type 1 of a short type 1 block. So it sort of destroys a short type 1 block. We keep applying these operations alternatively. So first plus, then up, then plus, then up, until we find an SG where the distance between AP and BP is 2 in this case. So here we have the vertex that is disjoint from AP and BP. And now what we are going to do is we're just going to go back. So the last thing that we did here was we made this Y place appear. So now this guy is going to move to the left. Everything from here to the right moves to the left, including this guy. And we get now this green vertex for this place here. Notice now that we have this intersection between the new vertex, which is going to be our Y vertex, and our blue vertex. This happens because we are using the slot of type 4 that we made appear. Next, we are going to go back this up operation. That means that we push everything from here to the left. Notice that this thing here doesn't produce any new intersections because we had a type 1 block with 2 squares, and we can only use one of them in our vertex. So that won't produce any intersections. And then we will go back up again, doing the opposite of that plus. and we get another intersection. So notice that the intersection between our green vertex and our blue and red vertices, the sum of both intersections, is at most the number of times that we did the plus operation. Because of that, and because of because of the bound that we gave for P based on the diameter tree graphs, is that we get the bound here. Now, when the case when the distance is 3, we again start doing plus arrow, and here what we get is A star and B star that are disjoint between them. One of them neighbors with A, the other neighbors with B. Now, what will happen is that when we go back from an up operation, we get an intersection between A and B. A star and B star. That is because we are using the two squares in the type 1 block, and now we have only one left. But when we go back from a plus operation, we don't get any new intersection because of type 4. We are not using the square. So this square, we are not using it because it's type 4, which means that here we don't get any new intersection. We go back up again from an up arrow operation, and again we had two white squares that we were using in the star vertices, so we have a star intersection. And again, when we go up from the plus operation, we don't get any intersections. So now the intersection between A star and B star is at most the number of up arrows, and that is what is giving us the upper bound that we have for this sort of graph. So now the theorem that I show you how to prove so far is this. The diameter is 2 if R is big, 3 if R is at least k minus 2. I didn't show you this, but this is trivial because it's easy to see that this is a cycle. And at most k minus R minus plus 1 in this other case. So I'm not going to stop too much, but this is the example, if you want to look at it, of two vertices that are at distance at this 3 when R is less than 2k minus 3. So this is actually an equality here. And I'm not showing this either, but you can show that the distance is at least 4, and this is a pretty easy and basic thing. So it's not a good lower bound. So what's next? It will be really nice to find a better lower bound for R for when R is between 2 and k minus 3. And we know in particular that the diameter of SG 2k plus 2k, so this will be the smallest possible R, is around 3/4 of k, and our bound is k minus 1. So there is some room for improvement there. And the other thing that we will want to do afterwards is study the diameter of stableness graphs. So these are obtained similarly to Shriver graphs, but instead of erasing vertices that have elements, consecutive elements, you erase vertices that have elements at distance less than or equal to s. And that's all. Thank you for your attention.
Thank you, Adrian. Is there any question? So maybe I have a question regarding this last, the previous slide, like whether you have some idea or maybe some conjecture about the bound.
So far, what we have been trying to do here, since we know that the diameter is 3/4 of k for this case, is we want to try to prove that the diameter, if you increase n, the diameter cannot increase, because this will give us another upper bound that is better than ours for around half of the cases. What we can do so far is prove that it can increase at most 1. But that is not so good. I actually think that yeah, that it cannot increase. And what I think is that's probably most of the time is going to be going down by 1, and in some cases it's going to be stable, but I don't really know where.
Thank you. So somebody else, any question?
Yes. Hi. How do you know that this 3-4 bound by computer, or you prove it?
So this comes from a different work, but a student of mine was studying these graphs, and she has an actual pretty good representation of them. So
Okay.
these guys here are a complete bipartite graph, and then below that you have a bunch of cycles, and the way that you connect is sort of straight down. So you have a complete bipartite graph on, say, on 2k plus 2 vertices. Each of them is connected straight down with a cycle and another cycle and another cycle and so on. The last cycle, you either get a smaller graph, so k plus 1 instead of 2k plus 2 with antipodals connected, or it's a big cycle, but the vertices are also, if it's big, then antipodals are connected. So if it's 2k plus 2, if it's small, then they are connected to antipodals of the previous cycle.
Okay.
So what will happen is that if you want to connect two vertices, you get two choices. You either go to the bipartite graph up here, connect, and then go down, or you go down to the bottom smaller cycle, use the antipodal, and then go up. So what happens here is that the vertices that are at the longest distance are the ones that are at level around 3/4 of k.
Okay.
So 1/4 of k away from the small cycle down here.
Perfect. Thank you.
Thank you.
Thank you, Adrian. So let's thank Adrian again.
Mami, ¿por qué aplauden tanto?
And so we can continue with our program. So to continue for the last talk of today, we have Daniel Quiroz. Okay, Daniel Quiroz is at the University of Valparaíso, and he will talk about immersions, complete click immersions and independence number. Sorry, I was translating directly from the Spanish and didn't really work. So thank you, Daniel.
Thank you, Andrea, and I thank you for the presentation. Thank you, and I for organizing, and thank you everybody for being here. So what I'm going to talk about is joint work with Sebastián Bustamante, Maya Stein, and Jose Zamora. So, oh wait, yeah. So let's just start with some basic definitions and mention a few things that Marthe already mentioned in her talk. So we're going to talk about our graphs are going to be finite and simple. And by omega of G, we're gonna denote the click number of G. So it's the largest number of vertices that induce a complete graph in G. And by chi of G, we're going to denote its chromatic number. Okay, so a trivial lower bound for the chromatic number would be omega of G, because, well, if you have a click subgraph which induces a a subgraph which induces a clique, then you need to color each vertex with a different color. So so if you have large omega, then large clique number, then you're going to have large chromatic number. So does it go the other way around? So if we have a large chromatic number, can we guarantee that we have a large clique subgraph? And the answer, as Marthe already mentioned, is an emphatic no. So Michalski, that was the year my father was born, showed that triangle-free graphs, so they don't have a triangle, so their clique number is 2, and they can have arbitrarily large chromatic number. Okay, so this fails very bad. So you cannot guarantee, if your chromatic number is large, you cannot guarantee that you have a large, even a triangle. Okay, but maybe let's not focus on clique subgraphs, but let's maybe focus on some different substructure. Okay, so does having large chromatic number guarantee some large complete substructure? And if we look at minors, then we are standing in front of Hadwiger's conjecture, which says that, which states that every graph contains a clique minor of the size its chromatic number, and this conjecture is trivial when your chromatic number is small, at most 3. It's not too hard when it's 4, but then it becomes really hard. So for 5, it's known for 5 and 6 as well, but these 2 cases depend on the 4-color theorem, and the dependence for the case equals 5 was proved by Wagner in 1937, and then Robertson, Seymour, and Thomas proved the case equals 6 using the 4-color theorem. And from then on, it's open. Okay. But we're asking perhaps a more humble question. Do we have some large complete substructure? And if we talk about minors, then the answer is in some way yes. Okay, so if we have a graph with a chromatic number at least t, then it contains a clique minor on t over ft, where t is on the order of square root of log t. And so that was proved by Thomas and Kostoshka independently in '84, and this has been recently improved, a major breakthrough by Noring, Postel, and Song, and then again further by Postel last year. But this f of t, despite this outstanding efforts, this f of t cannot be still. We cannot change this f of t by a constant. Yeah, the clique minor that we get is not a linear function. Its size is not its order is not a linear function of our chromatic number. Okay, so it would be really nice and a major breakthrough if one could change this f of t to a constant. But there is something. It's much better than subgraphs. Okay, so okay, Hadwiger's conjecture, it's hard. Here it is again. Sometimes it appears suddenly, but maybe we can consider a relaxation. So by alpha of g, let's denote the independence number of a graph. So by independence number, I mean the the largest size of a set of vertices that don't induce any edge. Okay, and an easy lower bound for the chromatic number of an n vertex graph is n over alpha. Well, because when you color the vertex of a graph, you are partitioning the vertex set into independent sets, and the least number of colors you can get is well, if all of them are as large as they can be. Okay, so it's hard to get a complete minor on chi of G vertices. So what about something that could potentially be less? And this is the conjecture of Duchet-Meiniel from 1982 that says that every graph contains a clique minor on an n over alpha vertices. And the nice thing about this conjecture is that they get, and the proof is quite short, that they get within a factor of 2 of that. Okay, so they proved that every graph contains a clique minor on n over 2 alpha vertices, which is very nice. But going beyond that, it would be quite hard. I think Jacob Fox proved that you can change that to by 1.96 or something like that, and it was later improved, but it's not much farther. So it's hard to get beyond this point. Okay, but the title of the talk involves graphs immersions, and this is what we're going to talk, not so much minors. So this is the complete substructure that we're going to talk about, and probably and it might be that you haven't heard of immersions ever, so I'm going to define what an immersion is. So a graph G is said to contain another graph as an immersion, a graph H as an immersion, if there is an injective function which maps the vertices of H to the vertices of G, such that for every edge in H, there is a path in G, which with the endpoints which are the images of U and B, yeah. And these paths are pairwise H disjoint. So this is best explained with a picture. So we have a graph G over here on the left, and a graph H over here. And we want to see that G contains H as an immersion. So we have our vertices U, V, and W, and we're going to map them to these vertices here. So this is going to be phi of U, phi of B, and down here phi of W. And for each edge in H, we need a path in G. So for this edge, this purple edge, we have this path. For this green edge between U and B, we have this path between the images of U and B, and so for this red edge, we have this path, and they are pairwise edge disjoint. So we have shown that G contains H as an immersion. And I'm not sure if you can see the colors there, but here we have another graph G, which contains a K4 as an immersion. And it's nice to see, and it's nice to notice that here what we did is on G we had 3 petals, and here on G prime we have 4 petals, and they're slightly thicker, and then we got a K4. And if you do that, if you add one more petal and you make the petals thicker, then you will get a K5, and you can do this and get any clique immersion you want, as big as you want. And the nice thing is that these flowers, if you want, they're planar. So what we're doing here is we're obtaining any clique immersion from planar graphs, which is does something that doesn't happen with minors, because minors planar graphs exclude K5. Okay, and just before I move on from this slide, the image of the vertices of H by our mapping will be called the branch vertices. So these are the branch vertices here. Just some important notation. So minors and immersions, well, they're really not comparable. Okay, so the class of planar graphs, as we just noticed, well, and by Quiroz theorem, excludes K5 as a minor, but contains all cliques as immersions. And for instance, the class of graphs with maximum degree at most 3, well, if you have maximum degree at most 3, you cannot have many edge disjoint paths going from your vertex. So it will exclude K5 as an immersion, but contain all cliques as minors. So minors and immersion are comparable, but they do share some similarities. Both of them are well quasi-orders, meaning that if you have an infinite set of graphs, then one is contained in the other by either of the relationships, say minor or say immersion. And this was, both the results were proved by Robinson Seymour. And if G contains H as a topological minor, then it contains H both as an immersion and as a minor. Okay, so they do share some similarities, and there is some hardware type conjecture for immersions as well. So can we have a complete large immersion if we have a large chromatic number? In fact, do we have a one of the size of the chromatic number? That's the conjecture of Lesky and Meiniel. So it's true for if the chromatic number is at most 7. So that's one more case than Hadwiger's conjecture, and the proofs are quite short and simple. And we have and there are some there are linear bounds on the size of the clique immersion you can guarantee. Okay, so so Devos, Dvorak, Fox, McDonald, Mohar, and Scheide, they prove that that if G contains an immersion of a clique on the chromatic number over 200 vertices. Okay, and Dvorak and Yepremian, they further improve this to show that that any graph G contains an immersion of a clique on the chromatic number over 11 vertices. And this was so the state of the art is that Gauthier, Lie, and Woolen, they prove that every graph contains a clique immersion on the chromatic number over 3.54 vertices. Okay, so that's how things stand there. But how about our relaxation? Yeah, the relaxation we consider with the independence number. Well, this result of Gauthier, Lie, and Woolen would imply the following, which is that every n vertex graph contains an immersion of a clique on n over 3.54 alpha vertices. Okay, but this problem was actually considered before the work of Gauthier, Lie, and Woolen by Vergara. And she proved that if your graph has independence number 2, then it contains a clique immersion on n over 3 vertices. So if you would change here this alpha by 2, then you would get something like 7. And she actually proves that you can do 3, n over 3. But Gauthier, Lie, and Woolen further improve this, and they prove that you can actually get a click immersion of on 2 times n over 5 vertices. So that's what was known for alpha equals 2. And what we proved is that if your independence number is larger than 2, if it's at least 3, then your n vertex graph will contain a click immersion on n over 2.25 alpha minus 1. It's so we improved this 3.54 by this 2.25 and a bit more. I'm actually hiding some constants there, but this is essentially it. Okay, so any questions so far?
So maybe one small question. Does this mean that actually the alpha equals 2 case is a little bit harder, like, or less is known for this case currently? Like the bound is a little weaker, it seems like. That's kind of surprising.
Oh, wait. So
I also might have just done 5 halves wrong in my head, so.
So I would say that case is actually harder. So well, I mean, harder in some way. So the techniques we use for our result would give would actually give the result of Vergara. Yeah. So to obtain the result of Gauthier, Lee, and Whelan, which by the way, Vergara's result was using a different technique. But the result of Gauthier, Lee, and Whelan needs a bit more care if you're only talking about alpha equals 2.
Okay, thanks.
Thank you. Okay. So let's try to prove this. And so we want to prove, and we want to focus on alpha equals 3. So we want to prove that every m vertex graph with alpha equals 3 contains an immersion on 2n over 9 vertices. And of course, I'm not going to focus only on, and I'm going to give you a hint on how you would approach it for larger alpha, which is also interesting. Okay, so we are going to do. So again, we're focusing only on alpha equals 3, and we're going to do induction on n. And the result is trivial whenever the amount of vertices, the click immersion we want is only a vertex. Yeah. Okay, so our graph has independence number 3. So there is some independence set, A1, A2, A3. And by induction hypothesis, if we take that independence set out of our graph, then we get a click immersion on 2 times n minus 3 over 9 vertices. So this is what our graph looks like. We have a graph. We take out this independent set. Then this is what we get is on this side, and we have we separate our graph into the branch vertices and the rest of which we call M, and the rest of the graph which we call Q. And that's mysterious, really. But that's what we did. So we call this M. So these are the branch vertices. So some of them might be joined by an edge, or some may have a path that goes through Q. And we want an immersion on this amount of vertices, 2n over 9. And it's easy to see that all we need to do is just add, since we have an immersion of this size, all we need to do is add 1 vertex to our branch vertex. Okay. And we're gonna pick one of these. Okay, so before doing that, we need some simple observations. The first one is that our independent set dominates the rest of the graph. That means that every vertex in the graph minus I has a neighbor in I. Why is that? Well, because if I had some vertex here that didn't see anyone here, then we would have an independent set of size 4. So our picture, the picture we had here, translates into this one because everybody is in the neighborhood of one of these. So M, you can see that every one of M is either on the neighborhood of A1, or on the neighborhood of A2, or on the neighborhood of A3, and there's nothing else in M. And the same for Q. Okay, then there comes the second simple observation, is that for every I, the non-neighborhood, this will denote, this N with the bar will be the non-neighborhood. The non-neighborhood of AI has independence number at most 2. Well, if it had independence number 3, for instance, it is the non-neighborhood of a vertex. So then you would have an independent set of size 4. Okay, so that cannot happen. So the non-neighborhood of every one of my vertex has an independence number at most 2, and the intersection of any 2 non-neighborhoods has independence number at most 1. So it's a clique, by the same reason. So how does it look? So say Q is, every vertex in Q is a neighbor of either 1 or 2 or 3, or maybe a couple of them, or all 3 of them. And what I'm saying is that this green bit, which is the non-neighborhood of 2, has independence number at most 2. Okay, and this red bit here, which is the non-neighborhood of 1 intersected with the non-neighborhood of 3, it's a clique. Okay, so this cannot be too large, because otherwise I found the clique immersion that I want. And this cannot be too large because this has independence number at most 2, and then I can use the result of Gauthier, Lie, and Whelan. Okay, so this green bit is not too large, and this red bit is not too large. So this bit here is large. And same if I only take these 2 petals or these 2 petals. So these bits need to be large. Okay. And in general, what we do is if we look beyond alpha equals 3, what we do is we use induction in alpha. So the non-neighborhoods and their intersections will have small independence number, and by induction they will have some large clique immersion. Okay. We're going back to the case alpha equals 3. Sorry. The path. So we're going to add 1 vertex, let's say A3, to our branch vertices, and what we need to do is find paths from every vertex in M to A3. So the paths that we're going to consider go from M to A1 to some vertex in Q, and then they could potentially go to A2 and back, and then to A3, or they could just go directly to A3. So those are the paths that we're going to consider. And the nice thing is that since they go through the intersection of the neighborhoods of the vertices outside, then we know they go through the paths, the sets in Q that are large. So we can potentially make lots of paths, and they are all disjoint from the paths that existed previously, because they don't go through Q or through M, and they're all edge disjoint between them. Yeah, this is easy to see from the picture. So the hard thing to do is to see that there are enough paths. So what we do is we create an auxiliary graph which contains all our useful vertices on this side of the graph, on G minus I. And and what I mean by useful, well, we definitely need these ones, the ones on M, and we need the ones that are nice because they see two vertices in I, okay, or at least two. And they will be joined by an edge if they have a common neighbor in I. So for instance, this vertex here and this vertex here, they have a common neighbor, which is A2. They have a common neighbor in I, so they will be joined by an edge. And then what we need to do then is just find vertex disjoint paths on our auxiliary path graph, and by that, and to do that, we use a Menger's theorem, and we know that the size of our cuts are going to be large enough. So we have them characterized, and you can play with that and see that your minimal cut is going to be large enough for what you want. And one thing that you might wonder is, where does this 2.25 come from? Well, you want to make your click immersion as big as possible, but if you make this too big, then this bit is not going to be big enough for your paths. Okay, so your cuts are going to be smaller than what you want them, and you're not going to be able to. And by balancing that, you get this 2.25. And I'm out of time already, so well, I mean, so I'm just going to finish with this open problem, which is the case alpha equals 2. So this case is, I mean, for Hadwiger's conjecture is a very interesting case. For the immersion conjecture is also very interesting, but it can be it seems hard, but it would be very interesting. And in particular, but not just, it's not interesting just for that, but in particular, since our proof works by induction on alpha, this would also, improving that case would improve all later cases. And thank you for listening.
Thank you, Daniel. Is there any question?
I have one small question. I'm just curious. If you could really resolve this case for alpha equals 2, what's the best that the constant would become in the case for larger alpha? I mean, if you don't know offhand, that's fine.
No, it's. I mean, you would replace this 2.25 by a 2.
Oh, okay.
Yeah.
All right. Cool.
So you wouldn't solve it. You would still need work.
Alas.
So if nobody else has a question now, and we can thank Daniel again. Thank you, Daniel. Well, thank you everybody to attend the first day of our thematic session in discrete mathematics. We had 3 very nice talks. I'm very grateful to you guys that were giving talks, very nice ones. And well, we see each other tomorrow, okay? Tomorrow at 4:15 p.m. Chilean time. So we will have again 3 talks, and so we see each other tomorrow. I will send you links so that you can easily find it, okay? So I will send through the mailing list of the ASCO or something like this. I reach you with the links so that you can just click there, and at 4:15 we see each other here, okay?
There are changes for tomorrow. Does everybody know? Tomorrow at the